we're going to talk about logarithmic functions. And logarithmic functions, they're basically like the inverse of exponential functions. So if you have an exponential expression, so we have, for an exponential expression, we have a base, we have a power or exponent, and then we have some result n. Well, this has what we would call a logarithmic equivalent. And it works like this. If this is true, then the following is also true. So the logarithm and the exponent, they're related this way. So if you have an exponential expression with a base b, an exponent p, and a result of n, then you have a logarithm also of base b. And the logarithm will give us, if we give it the result n, it'll give us that exponent, gives us the exponent back. So the exponential expression gives us the result, the logarithm takes the result and gives us the exponent. And the base is going to be the same. So to give a more solid example, two to the third is equal to 8. Then the logarithmic version of this relationship, you have a base 2. So that means we have a log of base 2. The log will always take the result, and it will give us the exponent. Now, another way you could look at this, you can see the exponent expression in the log. 2 with an exponent of 3 will give you 8. Sort of counterclockwise rotation. 2 to the 3 equals 8. So, for example, let's say you have this. Log base 1/2. If you want to write this as an exponent form, 2 to the second power gives you 1/4. So the base is still the base. The exponent, and sure enough, this is true, 2 to the second gives you 1/4. Or 1/2 to the second gives you 1/4. And so you might see something like this. We can do another one. So with log base 5 of 125 is equal to y, well, this is the same as saying 5 to the y is 125. And we might try to solve for y by guessing, well, what exponent could you put here for y, where 5 to that exponent gives you 125? In this case, it would be 3. 5 to the 3 would give you 125, so y would equal 30. All right. So let's try another one. So the cube root of 8 is equal to 2. Now, cube root, what this means, and just to recall, the nth root of some number m is m to the 1 over m. So here we would have 8 to the 1 over 3 is equal to 2. So with logarithm, we're still going to have a base of 8. The base of the exponent will also be the base of the logarithm. And then the Exponential function takes the exponent as the input and then gives a result as an output. For logarithm, we take the result as input and the exponent becomes the output. And you can check this. 8 to the 1/3 gives you 2. Or the cube root of 8 is 2. Or the logarithm base 8 of 2 is 1/3. Now, I said something there you might have picked up on. Let's say we have this. Y equals b to the x. So let's put together the equivalent logarithmic expression. Well, that means log of the same base. And remember, with the log, we take the output, or the result, and then we have the exponent is what we kick out. And notice what's going on here. Input x is now output for the logarithm. Output y is now input for the logarithm. So when we work with the exponent functions and logarithmic functions, we're switching the inputs and outputs. And that happens with inverse functions. So this is what we've got. So f of x equals b to the x. And g of x equals log base b of x. These are inverse functions of each other. So one will undo the other. So what this means is this. Let's say we have f of x equals 2 to the x. And then we come up with a g of x, which is log base 2 of x. Well, these two functions are going to be inverses of each other. Got the base, 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 and the base. Now the bases have to be the same. If this is, since this is base 2, if this was base 3, they wouldn't be inverses of each other. You've got to have the same base here. So what this says is this. F of x, or let's take composition here. F of g of x. Will this be 2 to the g of x? Which is going to give us 2 log base 2 of x. And what this says is when we have the bases matching, these cancel because they're inverses. And that has to leave us x. Because again, with inverse functions, f composed of g, if they're inverses of each other, we should get x at the end. So since we figured out they're inverses, if we put one function inside the other, we've got to end up with x. So when we see this, an exponent base and a log base like this, they're going to cancel. So also if we do this, g of f of x, this would be log base 2 of, log base 2 of f of x, or log base 2 of 2 to the x. And again, because they're inverses, everything needs to cancel, leaving an x. So when we see a log base 2 and an exponent base 2, they go away. And according to our rules with inverses, the composition should end in x. So this is what we get. We get an important property here. Log base b of b to the x just equals x. And again, because these functions are inverses of each other. And b, so the log base b of x is x. Again, because exponential function and log function are inverses as long as the bases match. All right. So let me do some examples with these. Now, we could use, I'm sorry, let me back up. Let me not go this way, go this way. There we go. So we want to evaluate this. What is this equal to? Well, we can rewrite this as log 7, and 49 is 7 squared. So what we basically have is a situation where log base 7, 7 to the x. Now we've given a number for x. But we're still going to get cancellation. The log in its base and the exponent base are going to cancel, and we're just going to get 2. So let's take a look at another one. Now we actually do have two functions here. This would be 7, and this would be playing the role of x. And this is log base 7, and this is playing the role of an x. But this exponential function, because the base of the exponential function and the base of the logarithm match, they're going to cancel. Base of the exponential function, log and its base will go away, and we're just going to get 23. And again, this only happens because the exponential function base and the log base are the same. Let's take a look at another one. So let's say we're supposed to evaluate this. Well, let's simplify this. Let's try to turn this into an exponential function. Is there some way we can turn this into 3 with an exponent of some number? Can we do that? Well, 1 over square root 3. Remember, square roots are just exponents of 1/2. So this would be 1 over 3 to the 1/2. And this is below a 1. Let's rewrite this with a negative exponent. Because 3 to the negative half, that means take the reciprocal to get this. So let's just go backwards. Start out with this and go to here. And so now we've got 3 to the negative half. So we can rewrite this problem as log base 3, 3 to the negative half. And what's going to happen? The log with its base, the base of the exponential function, they're going to go away. Negative half. All right. Now, we do have some special properties with logarithms. And we'll talk about limitations on the logarithmic function also. First off, let's look at some properties. Log base b of 1 is equal to 0. Now, why is this true? Well, the reason is, if we think about what this represents, b to the 0 equals 1. So any number to the 0, other than 0 itself, is going to give you 1. So whatever number we choose for the base, and just to recall something, this is the inverse function for the exponential function. You might recall we had some limitations on the base for the exponential function. We said b had to be greater than 0, no negative bases, no 0 bases, and b, the base was not equal to 1. So we're going to inherit those same restrictions here with our logarithm. So in this case, though, we're going to consider b just greater than 0. So b to the 0 gives you 1. And that's always going to be the case, regardless of what we choose for b. Now, we also get something like this. The logarithm of b to the b equals 1. And we can also justify this by saying any number to the first power gives you that same number. Now, those are sort of the major other properties to consider. And then, of course, we've looked at our inverse properties. Now, we do want to talk about the restrictions on b. That is going to be important. And they're going to be the same as we had for the exponential function. So for f of x equals log base b of x, we're going to get these restrictions. B, the base, is greater than 0, and b is going to not be equal to 1. Because again, this is the same base that we were working with the exponential function. So the restrictions on that function, we're going to inherit those with this here, the base for the logarithm. Now, x has some restrictions also. X is going to be greater than 0. So this is going to have some interesting effects on the graph for this. We better take a look at that. What does the graph of this look like? Well, if we recall, for an inverse function, it's reflected over the line y equals x. And that gives you the inverse function. So for example, recall, let's say we have a positive square root function, then the inverse of this is going to do something like this. And this is a reflection across the line y equals x. So we could use the reflection technique to construct this function. But we're going to do it computationally. We're going to come up with a technique, and we're going to use those three numbers that were so helpful with working with exponential functions, -1, 0, and 1. The difference is going to be this, though. We use -1, 0, and 1 as inputs. Now we're going to use them as outputs. Now, we're going to still have the two cases. What happens with b? B's not going to be equal to 1, and it's got to be greater than 0. So we're going to consider the first case. B greater than 1. So what we're going to have is this. We're going to start with our output as -1, 0, and 1. And we're going to ask the question, what would the input be? So let's choose a base. We've got to come up with a base. So let's go with a base of 2. Just like we did with the exponential function. We have a base of 2. So we know what the output is. We want to figure what the input was. And let's call this x. So if log base 2 of x gave us -1, well then how do we find x? Well, remember how we do this. This says 2 to the -1 equals the result. So we use that relationship between the logarithm and the exponential function to get this. And 2 to the -1 is 1 over 2. So we're going to get 1/2. So that's how we figured it out. Now let's go with 0. So we have log base 2 of x. Well, now the output is 0. So you say 2 to the 0 gives us x. Or in anything to the 0 power that is 0 is going to be 1. So x is 1. And then finally, we have an output of 1. So to find the input, we go 2 to the 1 equals x. Or 2 equals x. So in this case, and this is what you would expect with inverses, we use -1, 0, and 1 as the inputs for the exponential function. Well, because these are inverse functions, we're going to use the inputs now as outputs. The role of input and output switches. So now they're the -1, 0, and 1 outputs. And if you recall from the exponential function, we also derived the graph of an exponential function with a base 2. And the output, when the input was -1 for the exponential function, input -1, we got 1/2. Input of 0, we got 1, and an input of 1, we got 2. So for the inverse logarithm, the inputs and outputs switch. Now the input is 1/2, the output's -1. The input is 1, the output is 0. The input is 2, the output is 1. So the x and y coordinates switch, which is what we expect with inverse functions. So I'm going to write these up here, and now we're going to graph a line, or our function rather. -1, 0, and 1. We have 1, we have 2, and there's 1/2. So first off, -1.5. Or sorry, 1/2 and -1. So that puts us right here. Then we have 1, 0, which puts us here. And then 2, 1, which puts us right there. And so what we're going to get is a function that does this. And it has an asymptote, and it's vertical. So this is going to be the function f of x is log base 2 of x. And that's what it looks like. Now, in general, we're going to have the same sort of shape for functions that have a base bigger than 1. And now you remember with the exponential function, regardless of what the base was, the graph would always pass through the point 0, 1. With the logarithm, we're going to see our graphs pass all of them through 1, 0, unless we've done some translations or transformations. So in general, what we're going to get for b greater than 1, we have -1, 1 over b, 1 and 0, and b and 1. And the vertical asymptote. So in general, that's what we're going to get. So this is the case when b is greater than 1. And this was also a case we looked at with the exponential function. But we also had a second case, and that was when b is between 0 and 1. So let's take a look at that. And again, just like with the exponential function, we're going to use a base of 1/2. And we're going to use the same approach as before. We're going to switch the inputs and outputs. So now the inputs will be -1, 0, 1. And then we're going to ask the question, well, how do you get an output of -1? What does x have to be? And we're going to use that relationship, that inverse relationship that the logarithm has with the exponential function to figure it out. So log 1/2 x, if this turns out to be -1, that means 1/2 to the -1 gives you x. Or 1 over 1/2 gives you x. Or divide 1 by 1/2, you get x is equal to 2. So x is 2. Now let's suppose you have an output of 0. So 1/2 to the 0 gives you x. And then anything to the 0 power, that's just 1 other than 0 itself. That's 1 equals x. There you go. Finally, log base a half of x gives you 1. Well, again, that means 1/2 to the 1 gives you x. And that just means x is just 1/2. So here are our points. And again, they're actually the same coordinates we got for 1/2 to the x power. It's just now the inputs and the outputs have been switched. So let me write these down and we'll graph them. So what do we have? Well, we have x is 2 and -1. So that's going to be here. 1 and 0. And then here's a half. And 1. Now the graph we're going to get is going to do this. And then with a vertical asymptote. So it doesn't cross the vertical asymptote. And this would be f of x log base 1/2 of x. So this is what these graphs are going to generally look like when you have a base that's between 0 and 1. So in general, this is what we're going to get. So -1 and 1 over b. Remember, b is now like a half or a third. So 1 over b, that's like dividing 1 by a half or dividing 1 by 1/3. So let me get something over here. We always pass through here 1 and 0, and then 1 over b. I'm sorry, this is just b. I apologize. This is b. B and 1 is going to be right here. So again, b is going to be some fraction between 0 and b, or some tiny number between 0 and 1. That means 1 over b is going to be a number bigger than 1. B itself is something smaller than 1. So we're going to get this. And that's what we're going to get from the graph. All right. So like the other ones, you can do transformations on these. And they're going to follow the same rules of transformations and translations that we've seen in the past. So let me do one of those here. Let's say we have this. And the key thing, just like with the exponential function, not only is the curve going to move, but your vertical asymptote is going to move with you and move basically the same way. So let's say we have something like this. Log base 2 of x plus 2. Now again, we want to start out with the canonical function, log base 2 of x. And we graphed that earlier, and this is what we had. And those are outputs, -1, 0, and 1. Well, I'm sorry, they're the inputs, but, well, actually, no, they are outputs. They are outputs. So we have 1, 2, and then a half as our inputs. So we have a point here, here, and here. And there's a base function. Now what this says is this. Since we're adding 2 to x, that means we're shifting to the left. Remember, when we subtract from x, we shift to the right. When we add to x, we shift to the left. And that means we're going to shift these base points 2 units over. So instead of being a half, we'll go to -1/2 to -1.5. Instead of being 1, we'll go from 1 to 0 to -1. And this point will go from 2 to 1 to x equals 0. But the vertical asymptote is going to shift also. It's going to go from x is 0 to x is 1, -1 to x is -2. So let's see what that looks like. So let's shift this point over. It's going to have a y value of -1, but we're going to shift it from a half. So we're starting here. We're going to go over 1. There's -1/2. And here's -1.5. So we're going to go over 1. Oh, sorry, over 1. And then over 2 to here. If you start at a half and go 2 units to the left, you'll end up at -1.5. This point, we start at 1 and 0, and we go 1, 2 spots over, like so. And then this point here, 2 and 1, we go 1, 2 spots over there, and there we have it. Finally, we take where the original vertical asymptote was, at x is 0, we go 1, 2 to x is -2. Now we connect our points. And finally, we have f of x is log base 2 of x plus 2. And there we go. We've translated our graph. So there are 2 basic logarithm. Oh, there's one thing I should mention about this function before we finish with the basic logarithms that and these are ones you see on calculators. We got to talk about domain. Now, with the domain of logarithm, we kind of treat it like we would the domain of square root, except the square root can have 0. You can take 0 as a value. Logarithm can't. We have to always be greater than 0. So for the domain, x is greater than 0. And that kind of makes sense when you think about the exponential function. Remember, for the exponential function, y equals b to the x, when we graph that, we got something like this. Always pass through 0, 1, and we have our horizontal asymptote. Now, the range on this is always going to be greater than 0 because it never crosses, never contacts the x-axis. This is a horizontal asymptote that this function never crosses or contacts. So the range for this infinity. So what happens with the logarithm, and again, I'm assuming that the base here is greater than 1. So I'm using the example where the base is greater than 1. So the range and domain switch. So that means for the logarithm, well, now it's going to be the domain where we see 0, infinity. And sure enough, we've got a vertical asymptote that says this function will never contact the y-axis. And the y-axis is where x equals 0. So the domain for this is x greater than 0. So what this means is if whatever we put in here, it also has to be greater than 0. So if we have f of x equals log base b of h of x, say we're taking logarithm of h of x, we're going to need h of x greater than 0. It's like saying that if you have a function inside the square root, that function needs to be greater than or equal to 0. Again, you can take the square root of 0. But here we're going to need whatever's on the inside, it's got to be greater than 0. Can't even equal 0. So for example, let's say we have this. And it doesn't matter what base we're working with, we're always going to have this requirement. So that means that this needs to be greater than 0. Subtract 6 from both sides, and this means x has to be greater than -6. So that means we have our -6. All the greater numbers are going to be to the right. And since we're greater than, not equal to, we're not going to include -6. And so what this interval is -6 infinity. And that's going to be our domain. Let me do another one. Let's see. Now again, the base isn't going to matter. We can have a long base 3/4. But the key thing is whatever's being given to this log, it's got to be greater than or equal. It's got to be greater than 0. Greater, not equal to. It's got to be greater than 0. So this means this has to be greater than 0. So what this is going to imply is, let's see, anything x minus 7, as long as it's not equal to 7, whether this is negative or positive on the inside, we're going to square it, and it's going to be positive. If we get a negative number in here, like 3 minus 7 is -4, we're going to square -4, make it in the 16. So really, any number you can pick for x is going to be fine. If it turns out to be negative in here, we're going to square it. We're going to make it positive. There is one number we have to be careful of, though, and that's 7 itself. So what we can do, if we set this equal to 0, square both sides, or square root both sides. Square root of 0 is just 0. We're going to get x equals 7. So we find out this is going to cause a problem only when x is 7, because when x is 7, this is going to be equal to 0. Now it's always going to be greater than 0 if x isn't 7. And again, you could choose x to be 0.00001, 0.00001 minus 7. Okay, it's going to be some negative number. But then we square that negative number, making it positive. And so we're going to be greater than 0. The problem is, when is this equal to 0? And that's where we got to take a look at when that happens. It happens when x is 7. So now this is a number we don't want. So we don't want x being 7. So this means that's going to be our domain. If we graph this, we get to use numbers above 7. We can use numbers below 7, but we can't actually use 7 itself. Another way you'll see this written is you'll see a hole placed here like a circle. So this interval is negative infinity to 7. This one is 7 to positive infinity. You can union those, and that's going to be your answer. All right. So one more I want to show you. I don't think they have this in the homework, but it's an interesting one. X squared plus 1. Now, what's the domain of this? Well, does this ever become negative? And the answer is, it isn't. This is always going to be greater than or equal to 0. And the reason is, any number you give x, any real number, you square it, it's going to become positive if we don't have a positive already. So this will always turn out to be positive. And so when you add a positive number to 1, you're always going to be greater than 0. So that's fine. Now, the smallest this could get is if you actually chose x to be 0. So 0 is neutral. It's not positive or negative. But if you choose x to be 0, x squared just becomes 0. 0 plus 1 is just 1. 1 again is greater than 0. So for this special expression, it's always going to be greater than 0. So that means we can't choose an x that will make this negative. We can't choose an x that makes the whole thing equal to 0. So this means all real numbers we can use. All right. So last couple things to mention, there's some special logarithms that are on your calculator. And they're the log base 10 and log base e. And this could be a little confusing. Log base 10 of x is often just written log of x. And when you look on your calculator, most scientific calculators, when you see just log, they mean log base 10. Now what's confusing about this, some computer applications, some programming languages, when they have log, plain log, they actually mean something other than base 10. What they mean is this. Log base e of x. And we often see this written as the natural log, or ln of x. This is why when you look on that ln button on your calculator, you'll see above it e to the x. If you hit shift ln or second ln, you'll get the e to the x. Again, e to the x and ln x, they're inverses of each other. ln is log base e, and e to the x is e to the x. It's a log function and an exponential function that have the same base of e. Now what's confusing is that some computer applications, some programming languages, will have log x, but it really is acting like this. It's acting as if it has a log base e. So for example, the R programming language for statistics, if you type in log, say, of 5, you're not going to be counting what's the log base 10 of 5. It's actually calculating log base e of 5. So you got to be careful of that. This one will sometimes mean this. But for our calculators, your typical scientific calculator, log base 10 is written like this. Log base e is written like that. And again, we're interested in base e because that special number, it comes out of a limit that we use for, well, financial formulas. If we want to compound interest infinitely, continuously, this number naturally comes out in that calculation. It comes up in a lot of other places too. It's sort of like the number pi. And so for that reason, since we do get an exponential function that has e in it, again, our compounded interest, where it's compounded continuously, we're going to be interested in maybe undoing that, taking the inverse of that. That means we need to have a log base e, and it's such an important log, we give it its own name, basically. So just some examples on how this will work. If you see, for example, log base 10, and again, this is the log on the scientific calculator. We can think of this as log base 10 of 100, or log base 10 of 10 squared. And the log in the base and the exponential base, again, they cancel out. They're inverses. And that leaves just 2. There we go. Likewise, if we have something like let's see, here is something like this. Well, this is the base of an exponential function, and this is a log base e. These will cancel out, and we're just going to get 300. There we go. Do at least a couple more here. Oh, here's a good one. So say we have something like this. Well, again, this is 10 is the base of an exponential function because we have an exponent here. We have a log base 10 cube root of x. So the exponential function part, the logarithm part, since they have the same base, they're going to cancel. And that's just going to leave cube root of x. Let's do one more. So again, what we want to try to do, let's try to turn this into e to some exponent. So what we can do, 1 over e to the 6, we can rewrite this as e to the minus 6. Because remember, when you have a minus, we just take the reciprocal and then we can drop the minus sign. We'll get something like this. So what we'll do is we'll just start with this. We'll go backwards. So now we have the natural log e to the minus 6. And again, this is log base e to the minus 6. We just have negative 6. And that's our answer. So basically, this gives us two properties, and we've seen this before, but we're just going to specify them for this. The log of 10 to the x, because this is log base 10, that'll just give us x. And then 10 to the log of x, this is again log base 10, that also just gives us x. Likewise, the natural log of e to the x, because this is log base e, that will just give us x. And e to the natural log of x, that'll just give us x. And that's it. So that's the introduction to logarithms. If you have any questions, let me know.